The purpose of this video is to get us ready for section 8.2 in our geometry book, which is on Pythagorean theorem. And we've worked a little bit with the Pythagorean theorem, but we're going to explore more about it in section 8.2. But in order to get ready for that, we need to be able to simplify radicals. And what do we mean by a radical? Well, a radical is just simply the square root of something, like the square root of, let's say, 40. For what we've been doing, we've been punching the square root of 40 in our calculator and getting some kind of decimal answer. So 6 point something, or whatever this comes out to be. But that's not necessarily always the best for us, is to put everything in a decimal. Sometimes we want to work with square roots. But the square root of 40 is kind of a big number to have under a square root sign. So we do what we call simplify the radical. And that is our goal when we do this, is we're going to try to get the number under the radical, which is that symbol. Try to get the number under the radical as small as possible. And in order to do that, I need to understand, first of all, what is meant by the term perfect square. Now, a perfect square is a number, let's try it this way. 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared would be 16, and so on. 5 squared, 25. We say that the numbers 1, 4, 9, 16, 25 are perfect squares. Because if we put them under a radical, the square root of 1, if we go backwards, is 1. The square root of 4 is 2. The square root of 9 would be 3. The square root of 16 would be 4. And of course, the square root of 25 would be 5. So the first 5 perfect numbers are 1, 4, 9, 16, and 25. Well, if we were to take that on out a little bit, then if we've got 1, 4, 9, 16, 25, we could add to that list 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, and 12 squared. And these would be the first 12 perfect numbers. Now, of course, there's more, and there's infinitely many more. But these 12 are the ones that we should have committed to memory, because we're going to use these 12 probably more than anything else, but obviously there's more. We'll use those 12 more than anything else in what we call simplifying radicals. So let's take a look at some examples of how to simplify a radical. Well, let's go back to our original problem, and that was to simplify radical 40. Okay, so the instructions would say simplify each radical. And we'll do several of them to get through the steps. So the first one was radical 40. What we're going to do is we are going to look to see if 40 is divisible by any of the perfect squares in our list above. And in looking through here, it looks like it's divisible by 4. So we would say that the square root of 40, and I like to do it with like a little tree, is the same thing as the square root of 4, because 4 goes into 40, times the square root of 10. Now, what is the square root of 4? Well, it's a perfect square. And up above, we can see if we go all the way up, the square root of 4 is 2. So I can say that the square root of 4 is nothing more than 2. And the square root of 10, we'll leave it right there for now, square root of 10. So we have broken down radical 40 has now become 2 times the square root of 10. They're the same thing. They're equal. Well, let's look at the square root of 10. Are there any numbers from our list up above that go into 10? Well, the only ones we can look at are those less than 10. 9 does not go into 10 perfectly. 4 does not go into 10 perfectly. And 1 obviously goes into 10, but that's not going to help us a whole lot. So the square root of 40 simplified is 2 times the square root of 10. Because the number underneath the radical, 10, that is as small as we can possibly get. I can't break 10 down into, there aren't any perfect squares that go into 10 that will allow me to break it down further. Let's try another example. Let's do the square root of, let's try 200. Again, what we're going to do is try and find any perfect squares that go into 200. And I can see right away that the square root of 200 is the same thing as the square root of 2 times the square root of 100. Because again, what is 2 times 10? Or I'm sorry, 2 times 100. 2 times 100 is 200. Which one of these then is a perfect square? Is it 2 or is it 100? No, the answer is it's 100. And what is the square root of 100? It is just 10. The square root of 2, I can't break it down any further, so it's just the square root of 2. And we would write this, we always write it with the whole number, that perfect square that came out, in front. So this would reduce to, or simplify to 10 square roots of 2, or 10 times radical 2, or 10 radical 2. Now that was good if you saw that 100 went into it. But let's do this again. Let's do the square root of 200. And you might have noticed that 4 goes into 200. So 200 to be the square root of 4 times the square root of 50, because 4 times 50 is 200. The square root of 4 is a perfect square. That's 2 square roots of 50, or 2 radical 50. But radical 50 is not broken down far enough. There's something else. There's a perfect square from that list above that will go into 50, and it is 25. 25 will go into 50. So radical 50 will break down even more. So this becomes 2 times. Radical 50 breaks down into radical 25 times radical 2. Or in other words, it's 2 times, what's the square root of 25? It's a nice and easy 5 times radical 2. And then 2 times 5, we can put that together. 2 times 5 is 10 times radical 2. And notice we end up with the same answer both ways. In fact, there was a third way to do it where we might have seen that 25 went into 200, but we would still have taken 2 steps, and regardless, we would have gotten down to the same thing, that the square root of 200 simplified is 10 radical 2. Let's try another one. This one's a little more difficult. Not that it's any more difficult to work, but that sometimes it's difficult to see if any perfect squares go into a number. So let's try 261. Well, we can start at the top and work our way down, seeing if 121 goes into 261, and it doesn't. We could then try 100. We know it doesn't go into 261. 81, does it go into 261? So we could work our way backwards. And if we work our way backwards, we ensure that we're going to find, eventually, the biggest perfect square that goes into 261. Or we could start and work our way this direction. Now, if we start small and work up, it's possible we may have to take 2 or 3 steps to simplify this radical. So I'm going to just go ahead and choose to work small. Now, I don't need to check 1. I don't need to check if 1 goes into it, because 1 always goes into it, and that doesn't help us. Let's try 4. Does 4 go into 261? And the answer is no. So let's try 9. Let's see if 9 goes into 261. And in fact, it does. 261 is 9 times 29. And what is the square root of 9? It's just 3. So we have 3 times the square root of 29. Now let's check 29. Any numbers go into 29? 1, of course, will, but we don't need to check it. 4 does not go into 29. 9 does not go into 29. 16 will not go into 29. And 25 won't go into 29. So the square root of 261 will simplify to 3 times the square root of 29. Now here's a problem that I see. I'm going to work the same problem this way. And we're going to do it kind of like one of our book problems where you have to find the error. As I will see this answer a lot. People will write this as 29 square roots of 9. I'll see that for an answer. I would also see answers such as square root of 9 times square root of 29. And some people will answer this as the square root of 29. Actually, let me take that one back. They'll answer it as 29 square roots of 3. That's the other answer I see sometimes. Well, let's look at these and see why they're wrong. First of all, in the first one, we got here, which is great. It's a good first step. However, we took the wrong number out of the radical. What I like to think about is this sometimes, and I don't know if this will help, but this is kind of the way I think about it, is if you're underneath the radical, you're in jail. So the 9's in jail, the 29's in jail. And the only way to get out of jail is to be perfect. So only perfect things get out of jail. So in other words, the 9 is a perfect number. It comes from our list of perfect numbers. So it gets out of jail. But it doesn't just get out of jail as 9. It gets out of jail as its square root. So that's why this square root of 9 became 3. It gets out of jail. The 29 is not perfect, so it has to stay in jail. So if I come over here, I can show that the 29 stays in jail. So I see people sometimes take the wrong number and try and get it out of jail. Other times, come over here and say the square root of 9 turns into the square root of 3. That's not accurate either, because the square root of 9 is not the square root of 3. The square root of 9 is just 3. It gets out of jail, so it's not underneath the radical anymore. Since 9 was perfect, it gets out of jail, and 3 is what we write outside. Okay, let's apply this a little bit to a Pythagorean theorem problem. And like I said, we're setting up the next section, but we already know how to use the Pythagorean theorem a little bit. What we want to do is use simplifying radicals in with our Pythagorean theorem. So let's say, for example, we have this right triangle, and we know this leg is 12, this leg is 8, and we're going to find the missing side. Well, we've done enough of these problems already to know that to use the Pythagorean theorem, we say a squared plus b squared equals c squared, or 8 squared plus 12 squared equals x squared in this problem, or 64 plus 144 equals x squared. So I'll move up here now, and 64 plus 144, it looks like that's 208 equals x squared. So x equals the square root of 208. Now I want to answer this in what we call simplest radical form. I don't want a decimal answer here. I want us to simplify it. So we need to find some of those perfect squares that go into 208. So I'm going to go ahead and start small this time. And I'm going to start checking, well, I know 1 I don't need to check. So let's check 4. Does 4 go into 208? And in fact, it does. 4 goes into 208 4 times, and it's 4 times 52. So it's a square root of 4 times the square root of 52. Now, the square root of 4, we know that to be perfect, so it gets out of jail. It is 2 times the square root of 52. So we've taken square root of 208 and reduced it to 2 radical 52. Now, we need to check 52. Do I know if that's in simplest form? So I'm going to start small again, and I'm going to check and see whether 4 goes into 52, starting with the smallest one, and it does. So this becomes 2 times the square root of 4 times the square root of 13. Well, 2 times the square root of 4 is 2 times 2 times radical 13, or that simplifies to 4 square roots, or 4 radical 13. So that would be in simplest form. Now, I didn't check the 13 because I know 13 is a prime number and nothing's going to go into 13. So in other words, if we go up and put this in the problem, then this triangle would have legs of 8 and 12, and its hypotenuse would have a length of 4 radical 13 in simplest radical form. So you're going to have some problems with the Pythagorean theorem where I don't want a decimal answer, but I want you to leave it in radical form.